Good morning. Welcome to a little discussion on electrostatic binding energy. This is a great opportunity to talk about electrostatic potential and how charges are put together. So we know that we can describe the potential for a single charge, a point charge, as this kq over r. We'll note that v is a function of overall position, of r vector, but v itself is a scalar quantity. And all that means is that in general we care where we are in space as a vector, but we only depend on distance from any given charge. That r is always 0. If it makes you feel better, put an absolute value around that r in a denominator. All right. So now take a look at that expression in equation 1. As r goes to infinity, as you get further and further away from that point charge, the electric potential becomes weaker and weaker and weaker. So we say that the potential at infinity, far away from that charge, goes to 0, and that will come in handy here. Because what we really want to be able to do is bring a charge in from somewhere far away and position it close to some charges of interest. Now, we describe this potential in a couple different ways. So one way is when we define the potential, we actually defined it in terms of the potential energy per unit charge. So if we bring a charge in from some position 1 to another position 2, so that's just my general notation to indicate that I'm looking between two different points, 1 and 2. If we bring a charge in from position 1 to position 2, the change in potential it experiences is equal to that change in potential energy between those 2 points divided by that charge q. And we saw back in class that we can write that potential energy as a as a charge, as an electric field dotted with a distance. And if you don't remember where this is coming from, this is because potential energy can be written. This change in potential energy looks like work done, or the negative of the work done, and work looks like force dotted with distance, and if we divide, and force is charge times the electric field, QE. So when we divide out that Q, we get rid of the Q from the QE term, and we just end up with this E dot delta S. And you've seen this before, we use this in lab. And so that we can, if we want to find the total work done, when we move a charge from one place to another, we can just take this term up here in equation 3 and multiply it through by Q. And then we just get this delta U over Q, and we get negative Q delta V delta V between 2 and 1. Alright, so what we want to do with this now is we just want to assemble a collection of charges. And here I've taken a collection of 3 charges and sketched in what those field lines may look like. And you may be able to guess from looking at this what the signs of those charges are. Take a moment and think about that for a second. You should be able to identify. Charge Q1, we see field lines radiating away from it, and therefore it must be positive. Q2, we see field lines radiating in towards it, therefore Q2 must be negative. And Q3, again, we see field lines radiating away from one another, it must be positive. Now that's kind of interesting. You've seen this, we've seen these field lines bend in lab. This is the other thing that happens when we have positive charges. In positive charges, the lines sort of bend away from each other like this. So what we're going to do is we're going to take this, we're going to bring these charges in one by one. Now, with no charges, with empty space, we're going to bring Q1 from very far away into this empty space. At no point along the way does Q1 experience an electric field. There's no electric field at infinity. Infinity, in this context, by definition, means that there's no charges anywhere near. Everything is infinitely spread out from one another. So Q1 is very, very far away from anything else. When we bring it into this space, there's nothing here. There's no electric field. There's no potential. So essentially, from infinity to its location, where it's going to be at position 1, we see this Q1 times 0 minus 0. Come back here for a moment. Remember, the work done is equal to the negative of the charge that we're moving multiplied by the change in potential between those points. The potential at infinity is 0. Potential at infinity is 0. The potential at our current point is 0 because there's nothing there. So it takes no work. We can move that charge around all we want. And it takes no effort at all. When we bring in a second charge, on the other hand, the situation's a little bit different, because while Q2 starts out at infinity where there's no potential, it ends up near Q1 where there is a potential difference. Now, I must apologize here. I realize that I have written this term backwards. This should be reversed, because when we write delta V, it should be final minus initial. The initial position is at infinity, which is 0. The final position looks like that Q1 over R21 term. So these two terms are reversed, and the sign of this is incorrect. I apologize for that, and I just realized it now, and I don't want to start and remake the video or go and do edits, so I'm just telling you to fix that in your notes. When we bring a second charge in, we bring our third charge in, it's going to experience the field due to these other two charges. And so it's going to see the same thing we saw in that previous slide, but now with two charges. We bring Q3 in, and you see I've made the same mistake here. These two terms should be reversed. These two terms should be reversed. And I've left off K's. So we end up with a KQ1 Q3 over R31, a KQ2 Q3 over R32. If I insert the missing K constants, and R31 and R32 describe the distance between charge 3 and charge 2, charge 3 and charge 1. So then we want to assemble this whole collection of 3 charges. All we need to do is add up all the works done in moving each individual charge to this center location. So the total work done to assemble this is the work it takes to move 1 in the position, plus the work it takes to move 2 in position, plus the work it takes to move 3 in position. 1 we got for free, 2 just moved against 1 charge, 3 moved against 2 charges, moved in the field produced by 2 charges. Now, you can see that the more charges you have, the more terms you have, and each term has in it included more terms as well. So calculating this assembly can be complicated, and in general, we as physicists will look at large distributions of charge where we just do an integration over all these things. But at this level, we can keep it nice and simple and do small numbers of charges. Now, one of the things we're going to note is that if all of the charges have the same sign, then it's going to take increasingly more work to assemble a collection, because basically each of these terms will have the same sign, so they just add together. And so it takes a lot of energy to assemble a large collection of equivalent charges, or of same sign charges. On the other hand, if the charges alternate, if we have some positives and some negatives, then these terms can reduce each other. Some of these things will be positive, some of these things will be negative, and so that can keep it fairly small. And so it can be much easier to put together alternating charges, or charges of different sign. Now, that total work that you do to assemble a collection of charges is related to how that collection of charges is bound together. Remember conservation of energy. Delta K plus delta U is equal to 0 in the absence of non-conservative forces, when there's no non-conservative forces present. The total work, the work done is equal to the negative of the change in potential energy. So we can kind of rewrite this equation, this delta K plus delta U equals 0, and replace delta U with a negative W, a negative work. So we can write this, and then of course we get down to this point, which is just essentially our work energy theorem, that the change in kinetic energy is equal to the work done. So here's what we're going to do. Let's think of assembling a collection of charges, and it's taken us work W to do it. We're going to hold them at rest for a minute, and then we're going to let go. What happens? So, because we're holding them at rest, the initial kinetic energy is equal to 0. Well, if the total work done is greater than 0, that means that when we let them go, the change in kinetic energy will be greater than 0. Since they're starting at rest, this tells us that particles have to fly apart from one another. They're not bound together. All right, how do we do positive work? We have to push things in the direction that they are going, or in the direction we want them to move. That's how we do positive work. When we lift a box against gravity, we are exerting a force in the direction that we want it to move. When we lower a box, we're exerting a force in the opposite direction of that we're moving the box. We're pushing up weakly and letting the box move down, but we're not just letting the box fall. That would be negative work. All right, so as these charges are, as we push these charges against the electric field that's produced by another positive charge, we have to do work to push them together. Positive work. So when we let them go from rest, when they're close together, that energy that we have stored in that configuration by putting these charges close together will be released. The charges will move apart quickly, the potential energy will fall, and the collection will scatter. On the other hand, if the total work done is negative, what happens? All right, total work done being negative means that we've had to exert a force opposite the direction of the displacement. So imagine bringing a positive charge close to a negative charge. We know that they attract one another. The positive charge that we're trying to move around is drawn to the negative, but we're not letting it just fly. We are moving it in slowly to this position. We are working against the tendency of the system to draw these two charges together. That's negative work. When we let go, that attractive force will draw those charges closer and closer together. All right, so come back and take a look. If the work is negative, that means the change in kinetic energy is negative, which is an odd thing, because if the change in kinetic energy is negative and the kinetic energy started at 0, it means we have to have less than 0 kinetic energy as time goes on, and that doesn't make any sense at all. Well, what happens here is that when these things are drawn together, the system does work in a way that makes making the total work done being negative. Essentially, what's happening is the potential energy is dropping below 0. That's all right. We're good with that. The potential energy will drop further still. The kinetic energy will increase, but the particles will be drawn closer together. So the long and the short of this is, if we have to do work, if there's positive work done in assembling the collection of charges, then the system would fly apart if we let go, and we call the system unbound. If the system does the work, if we do negative work in assembling the collection of charges, then the system is basically stuck together. It will not fly apart, and that system is bound. So let's try doing a little calculation here. Let's actually try this whole thing out and see how this works. So I've got a collection of charges here. Q1 is a positive 2 nanocoulombs, and 2, 3, and 4 are all equal charges. They are all negative 1 nanocoulomb, and they're symmetrically spaced, so that each of the charges 2, 3, and 4 are a distance L, 1 centimeter away from one another, away from charge Q1, and there is an angle of 120 degrees between Q2 and Q4, between Q3 and Q4, between Q2 and Q3, as viewed from charge Q1. So we have a symmetric sort of a symmetric distribution here. And I want to know how much work it takes to assemble this collection of charges and whether or not the collection is bound. Okay, so again, let's think how we set this up. The first charge is free. We can move Q1 in here, or any one. It doesn't matter which one we move in first. It turns out that if no matter where we start, no matter which charge we start with or which order we go in, the total work done will always be the same. The work done in each step may not be the same, but the total work done will always be the same. So let's just start by moving Q1 in first, and we get that one for free. And then we need to move each of the other ones in here. So we're going to have the total work done being equal to the work done to move charge 1 plus the work done to move charge 2 plus 3 plus 4. Alright, so we know that work 1 is equal to 0 joules. That's easy. What about the others? Well, let's bring Q2 in. Now when we bring Q2 in, only 1 is present. And so there's only this one potential due to charge 1. And here I've actually gotten it right, and there's a minus 0 as we move it in from infinity, and I didn't remember the case this time, so at least I improved. When we bring charge 3 in, we now have to deal with both charges 1 and 2. And you can set this up. We have that first term in the square brackets here is the potential field due to charge 1. We're only a distance L away from charge 1 as we bring 3 in. And for Q2, we're a distance 2L sine theta, where theta is equal to 60 degrees. Check this out. Make sure you can see why that distance, so that distance is this distance over here between 2 and 3. I'm telling you that that's 2L sine theta. You should be able to do the math and figure that out. Think about that for a little bit, work on that, and make sure you can verify it. I'll wait. Pause the video. Alright, if you haven't figured it out, let's take a look at this. Clearly the distance between 2 and 3 and the distance between 3 and 4 has to be the same. This is a symmetric distribution. So let's just think about this. Think about the right triangle right here. The length of this leg of the right triangle must be L sine 60 degrees. So, because this length and this length are the same, the total length here must be 2L sine 60 degrees, 2L sine theta. And that's where that comes from. Alright, let's move in Q4. Again, try, if you didn't figure these out on your own so far by pausing and working on it, see if you can figure out the total work done to move Q4 into place, symbolically, like this. I'll wait. You pause. And when you're ready, you can start up again. Okay, I assume that you've gotten, hopefully you've figured out what work 4 is going to look like. It turns out 4 is going to have a term that looks just like this, the Q1 over L, because you're moving the same distance away from Q1. It's going to have another term that looks like Q2. We're moving it into the same position against Q2, and we're moving into the same distance against Q3. So we actually have two terms that look like this. So what we should see is this. 4 in the field produced by 1, by 2, and by 3. So now we can just plug numbers in and add it all up. And it's going to look like this. I'm as excited to see all the numbers as you are. Alright, and we want to find the total work done. We're just going to add these terms together. Our 0 joules are negative 1.80 times 10 to the negative 6 joules. For work 3, negative 1.16 times 10 to the negative 6 joules. For work 4, negative 0.53 times 10 to the negative 6 joules. We add those four terms together, and we're going to have a total work done of negative 3.48 times 10 to the negative 6. So the system wants to draw these charges together It's pulling these things together. The total work done is negative. Essentially, the charges would come together on their own if we let them, and they will be bound. If we release them from this position, they would come closer together. Turns out they would not completely come to the same position. As they get closer and closer together, those electrons will start to repel one another more strongly. If we look at the total distribution of charge, the total amount of charge, we had plus 2 nanocoulombs of positive charge, we had minus 3 nanocoulombs of negative charge. And so we shouldn't be surprised that negative 3 will dominate over the plus 2 eventually when you get close enough, and these things will repel each other, but they will not repel each other. They will not fly apart from one another. They will find their distance, essentially, and we can calculate what that is, but that's beyond the scope of what we're trying to do in this lecture. All right, so now we know how to calculate. We can calculate potentials at a given point due to a distribution of charges, and we can calculate how much work it takes to draw these charges in from infinity and put them together in one localized area, and we can determine whether or not that distribution is bound or not. Take a look at the homework problems and ask me if you have any questions. Have a great weekend, guys.